Okay, welcome back. So now in part two, we're going to talk about atomic absorption and emission. And what this is really about is, at a fundamental level, this is going to allow us to understand the interaction of matter and electromagnetic radiation, which is a really, as I said, fundamental and profound phenomenon. It's incredibly important to understand this. Energy, a lot of energy is exchanged in and out of matter this way. And so, if you can follow this, if you get an understanding of this topic of atomic absorption and emission, you are in a position to understand a great deal of phenomena in the world. Sorry. So here we go. All right. So we saw earlier that if you've got a source of white light and you run it through a prism of some sort that can deconvolute the wavelengths in that light, you get a nice continuous rainbow spectrum. Okay. However, back in the 1700s and 1800s, scientists in a lot of different laboratories were experimenting with these glass tubes that contained different kinds of gases. So, for example, in this illustration, here's a glass tube. They took all the air out of it, okay, to produce something close to a vacuum, and then what they replaced the air with was pure hydrogen gas, and then they sealed the tube. Put electrodes at either end, and they passed a current through the tube using high voltage. And when they did that, the tube and the gas specifically would glow. And so they were like, oh, well, here's another light source. Let's run it through a prism, because that's kind of what they were doing at that time. And when they did, they were really shocked to see that rather than getting a continuous spectrum, they got what you might call a discontinuous spectrum, or a discrete spectrum, so that you'd have one little ray of light that would be violet, one ray that was kind of a dark blue, and then a kind of a light blue, green, and red. And then if you project those colors as lines, so on a screen they would show up like this up here, like these discrete lines, each at a different wavelength. And they called these line emission spectra, okay, because you get a bunch of lines, and it's the result of atomic emission. And this was quite the mystery for many years. Scientists really had no explanation for why the light coming out of these excited hydrogen atoms would produce anything other than a continuous spectrum. It just didn't make sense. Okay, I'm going to skip this. This is just a little bit more detail. Turns out, okay, so here is the complete emission spectrum for the element hydrogen, at least in the visible part of the spectrum. So you've got four pretty pronounced lines: violet, blue, green, and kind of reddish orange. And these are the wavelengths where they appear. How about Mercury? Okay, here is the corresponding emission spectrum for Mercury, and here's an emission spectrum for neon. And you can see that neon is much more complicated than hydrogen. You might not be surprised, because neon has a lot more electrons, and it's a more complicated atom than hydrogen, certainly. So anyway, the point I want to make on this slide is that the atomic emission spectrum for an element provides kind of a fingerprint. It provides a unique signature for that element. And so it's, you can imagine this is a really powerful tool in terms of analyzing samples. Like if you get a chemical sample from somewhere, and you want to maybe analyze what elements are in it. You know, this is one type of spectroscopy that would allow you to uniquely identify the different elements in that sample. Okay, well, so scientists were very, very perplexed about why these line spectra. You know, what would explain that? And so, a very, very brilliant theoretician, a physicist named Niels Bohr from Denmark, he had been poring over the literature on these line spectra that were being reported from labs around Europe, and he set to work on trying to provide a model, an explanation that would explain why we get these line spectra. And so here it's a little bit of a cartoonish look, but here's basically what Bohr came up with. He theorized that an atom was kind of like a mini solar system where the nucleus is in the middle, like the sun, and the electrons were in orbits around the nucleus. Okay, so they orbited the nucleus much like planets would orbit the sun. And so let's consider hydrogen, because this is the element that Bohr that he was working on and that he was successful in describing through a model. So he said that electrons in an atom like hydrogen could orbit the nucleus in very specific orbits. So they could be, say, in the E1, the first energy level, or they could be up here in the second energy level or the third, and there's higher ones that I'm not showing. But the point is that they cannot be out here somewhere between E1 and E2. That was sort of not allowed. But they had these very discrete, what we would come to describe as quantized energy levels. Okay, so it could only be here, here, or here, let's say. And associated with each of those three orbits were three different energies. So if we assign the energy of the first orbit to 0, okay, so if you're in this lowest orbit, let's say that's 0 energy, then here are some examples of what the energies might be for the second and the third. I'm sorry, these are in joules. My unit got cut off here, but those are joules. Okay, so now furthermore, what he said was you could promote an electron from the first energy level to a higher energy level, but only if you supplied just the right amount of energy. So if you wanted to promote the electron from E1 up to E2, well, you would have to supply exactly 4.97 times 10 to the 19th joules. Oops, sorry about that, folks. So that is, if you hit this, you know, if there was some way of delivering an energy packet to this atom where the energy was just a little less than 4.97 times 10 to the 19th, you would not promote that electron up to the n equals 2 level. And also, if you delivered an amount of energy that was just a little bit too much, again, you're not going to be able to promote that. It's got to be just right. Okay, it has to correspond to exactly this energy difference. All right. Now, to connect this to what we've been doing over the last several days, you know that there's a relationship between the frequency of a photon and the energy. Okay, and here it is. Now, instead of just E equals h times nu, I'm putting a delta here. Delta means difference, and that energy difference between levels 1 and 2 is, you could graphically represent it like this, like the arrow. So here comes Mr. Photon, right? How are we going to deliver the energy that we need? Well, a photon turns out is a very good vehicle for delivering the kind of energy that we need. So if this photon has just the right frequency such that the energy delivered is 4.97 times 10 to the minus 19 joules, then we will promote this electron from the E1 energy state, which we call the ground state, into an excited state. Okay, so here comes Mr. Photon, and indeed we were able to deliver just the right amount of energy, and so we promoted it from the ground state, which is the lowest energy level, up to the E2, which is one of the excited states. Okay, great. Now, like the saying goes, what goes up must come down. And so the atom will remain in an excited state for a while, and it's hard to predict exactly how long any individual atom will stay in an excited state, but eventually that electron is going to come down, but in order to do that, it has to get rid of that extra energy that it just absorbed. Okay, and it does that through what we call atomic emission. And so what happens is a photon is given off, and the photon is going to contain exactly the same amount of energy that it took to get it from N1 to N2 in the first place. It's just that instead of absorbing that much energy, it's getting emitted. And yeah, and it has to, it's going to adhere to this same relationship. Now, this leads into your next problem set, where we're going to, you're going to get some practice looking at different transitions between different different levels, and you're going to be calculating the delta energy between those levels, calculating their frequency and wavelength, and then you're going to predict, you're going to determine what type of radiation that is by the emitted photon, and then the corresponding color if it's in the visible part of the spectrum. Okay, so that's it. So listen, thanks a lot for your time, and we'll see you tomorrow.